Pick a whole number, any one you like, say 10. Now double it to get 20, and look at the stretch of numbers in between, 11 through 20. Somewhere inside that window sits a prime. In this case there are several, 11, 13, 17, 19, all of them divisible by nothing but themselves and 1. Try it with a smaller number. Take 5, double it to 10, and check the window from 6 to 10. The number 7 is sitting right there, a prime. Take 100, double it to 200, and the gap from 101 to 200 holds 21 different primes. Every example lands the same way. You pick a number, you double it, and the space between is never empty of primes. That is a strong claim once you say it out loud. Between any number and its double, there is always at least one prime, with no exceptions ever, all the way up the number line forever. It has a name. It is called Bertrand's postulate. And the surprising part is not that it is usually true, it is that it is always true, and you can actually prove it. By the end of this, you will see the engine that forces a prime into every one of these windows. Here is why the claim has no business being true. The primes get rarer the higher you count, and you can watch it happen. Up to 100, a quarter of the numbers are prime. Up to 1,000, only about 1 in 6. Out past 1,000,000, fewer than one number in 12. The deeper you go, the wider the empty stretches get, and those stretches have no upper limit. You can find a run of 100 numbers in a row with not a single prime among them, then 1,000 in a row, then as long a desert as you care to ask for. Primes are out there, but they are spread thinner and thinner. So picture a window that keeps doubling in width. From 10 to 20, it is 10 numbers wide. From 1,000,000 to 2,000,000, it is 1,000,000 numbers wide. The window grows, which sounds like it should help, but the primes inside it are thinning out at the same time, fighting the window's growth. It is a genuine race, scarcity against width, and there is no obvious reason width should win every single round, in every window, forever. If the primes ever thinned out just a little faster than the window grew, one of these gaps would come up empty and the whole claim would collapse. The remarkable thing is that it never does, and we want to know what guarantees that. Before any clever argument, it is worth just checking, because checking is honest and it sharpens the question. So take every starting number from 1 upward and find the smallest prime that lands in its doubling window. For 1, the window reaches up to 2, and 2 itself is prime. For 2, the window goes to 4, and 3 is in it. For 3, 5 shows up. For 5, 7. For 7, the smallest prime in the window is 11. For 25, it is 29. You can keep going, and a computer will, for thousands of starting numbers in a row. We checked every starting number, up to 2,000, and a prime turned up in the window every single time, with not one miss. And it is not barely scraping by. Count how many primes are actually in each window, and the count climbs. The window after 10 holds 4 primes. After 50, 10 primes. After 500, 73 of them. The window after 1000 holds 135 primes. The tightest the supply ever gets is at the very bottom, where the smallest windows hold exactly 1, but checking is not proving. We tested 2,000 cases, and there are infinitely many we will never reach. A pattern that holds for the first 2,000 numbers can still break at the 2,001st, or a billion steps later. To know it holds everywhere, we need a reason, not a tally. The reason comes from a direction that looks completely unrelated. We are going to count the ways to choose a committee. Take 2 times your number of people, and choose exactly half of them to form a group. The number of distinct ways to do that is a famous quantity, written as 2n choose n, and it sits right in the middle of Pascal's triangle. For 2 people choosing 1, there are 2 ways. For 4 choosing 2, there are 6. For 6 choosing 3, 20. For 8 choosing 4, 70. For 10 choosing 5, 252. Now, why would committees have anything to do with primes? Because this counting number has a size we can pin down tightly from both sides, and its prime factors are forced to behave. Here is the size. This central number is always smaller than 4 raised to the power n, and it is always bigger than 4 to the n divided by 2n plus 1. So it is squeezed into a narrow band that grows like 4 to the n. For n equal to 4, the number is 70. 4 to the 4th is 256, and 256 over 9 is about 28. And 70 sits neatly between 28 and 256, exactly as promised. That squeeze is the whole foundation. We know almost exactly how big this number is. The trick now is to ask what it is built out of, because every whole number is built out of primes, and this one is no exception. So break the central number into its prime factors, and 3 clean facts fall out, each one easy to see, and each one doing real work. Take the case where n is 15. 2 times 15 is 30, and 30 choose 15 works out to be 155,117,520. Factor it, and you get 2 to the 4th times 3 squared times 5 times 17 times 19 times 23 times 29. Look at where those factors live. 17, 19, 23, and 29 are exactly the primes between 15 and 30, the doubling window itself. And each of them appears just once in the factorization, never squared, never cubed. That is the first fact. Any prime bigger than n, but no bigger than 2n, divides this number exactly one time. The second fact is what is missing. There is no prime between 10 and 15 in that list at all, even though 11 and 13 are primes, because primes in that particular band cancel themselves out completely and contribute nothing. And the third fact is about the small primes, the 2s and 3s. They can appear many times, but a prime can only pile up so high before its power climbs past 2n, and no prime power dividing this number is ever allowed to exceed 2n, so the small primes are capped. The middle band is empty, and the window primes each count exactly once. Keep those 3 in your hand. They are about to collide with the size we already know, and the collision is the proof. Now we set the 2 halves against each other, and watch what they force. We know the central number is at least 4 to the n over 2n plus 1, a real, sizable amount, and we know it is assembled entirely from the small primes, capped, plus the window primes, each used once. So suppose, just suppose, the doubling window held no primes at all. Then the only material left to build this large number would be the small primes, the ones up to 2n thirds, each one contributing at most a factor of 2n. There simply are not enough of those, and they are capped too low, to reach the size we prove the number has. The arithmetic does not balance. The supply of small factors falls short of the 4 to the n the number is guaranteed to hit. So the assumption breaks. There is no way to make the number big enough without borrowing at least one prime from the window. The window cannot be empty. For every large number, a prime is forced to exist between it and its double. Not because we found it, but because without it, the bookkeeping is impossible. That handles every large number in one stroke. The small cases, the first few dozen, you check by hand, and there is an elegant way to do it. Line up the primes 2, 3, 5, 7, 13, 23, 43, and on, where each one is less than twice the one before it. That overlapping chain blankets every small starting number with a prime in its window, no gaps. Large numbers handled by the squeeze, small numbers handled by the chain, and the claim is proved for all of them. This argument has a history worth knowing, because 3 different people brought it to where it stands. In 1845, a French mathematician named Joseph Bertrand noticed the pattern and stated it as a claim. He could not prove it, but he did something careful first. He checked it by hand for every number up to 3 million, and it held every time. That is why it carries his name and the slightly odd word postulate, a thing asserted while the proof is still owed. 7 years later, in 1852, the Russian mathematician Pafnuty Chebyshev proved it for real, settling the claim completely with a heavier analytic argument. For 80 years that was the state of the art, a true theorem with a demanding proof. Then in 1932, a 19-year-old named Paul Erdos published the argument we just walked through, the one built on the central binomial coefficient. It was his first published paper. It is elementary, in the technical sense that it leans on counting and simple bounds rather than deep machinery, and it is the proof mathematicians have loved ever since. Erdos summed the whole story up in a little rhyme. Chebyshev said it, and I say it again. There is always a prime between n and 2n. Step back, because the postulate is the flaw, and the truth is far more generous than the flaw. Bertrand's promise is only that the window holds at least one prime. 1. But we already saw the real counts run well ahead of that. The window after 10 has 4 primes, after 121, after 573, after 1135. The minimum, the closest the count ever comes to the bare promise of 1, happens only at the very smallest windows. Everywhere past the start, the windows are crowded. There is even a clean estimate for how many to expect. The count of primes in the doubling window grows roughly like n divided by the natural logarithm of n, climbing without bound as the window slides outward. So the gap between what Bertrand guaranteed, a single prime, and what is actually there, hundreds and then thousands of primes, only widens. And this is the resolution of the race we set up earlier. Yes, the primes thin out. Yes, any single number is less and less likely to be prime the higher you climb. But the doubling window grows so much faster than the primes thin that the count inside it runs away upward anyway, scarcer at every point, and yet more and more of them in every doubling window. Both true at once, and the postulate is just the easiest, lowest thing you can say about it. So that is the whole shape of it. Pick a number, double it, and a prime is waiting in between, every time, forever. The pattern looked like it had no right to hold, because the primes really do get rarer without end, and a doubling window really could have come up empty. What rescues it is not luck. It is a counting number from the middle of Pascal's triangle, squeezed so tightly between two known sizes that it has no choice but to hide a fresh prime in every window, just to be as large as it is required to be. A question about primes, answered by counting committees, and the same corner of mathematics that settled this so cleanly, is still full of questions nobody can answer. We know a prime always sits between n and 2n, but ask for a prime between consecutive squares, between n squared and n plus 1 squared, and no one has ever proved 1 is always there, though it certainly looks that way as far as anyone has checked. The window that doubles is tame enough to pin down. Pull the window tighter, and the same kind of question goes from settled to wide open. If there is one thing to carry away, it is that a pattern can look fragile, like it should fail somewhere out in the infinite and still be locked in place by an argument you can hold in your head. A 19-year-old saw that argument first. This was one more piece in a series on how one person settled one hard question. Stay for the rest.